So, all right, what's up, YouTube? So let's get started on the lecture. First thing I wanted to announce is that I just posted my incentive for course evaluations. So if you haven't filled out your course evaluation yet, first of all, get on that. Just do it. You should just do it because you want to provide feedback. I take the feedback seriously. I read through all the course evals. I've read through the midterm course evals this semester and made some adjustments based on those. I always read these and I do take these seriously. I want to know what you all think about the course, especially because I do some pretty different things in this course than most courses, and it's still fairly new. This is like the third semester I've been using this kind of a grading style, so I still want to know. I still want a lot of feedback on that because I'm really interested in how the grading style is perceived and this course structure is perceived by you, the students. Because I can speculate all day, but hearing it straight directly from you is the most effective way for me to learn about how this is working, and most importantly, how I can adjust it to improve even further next semester. You have the third iteration of this after me reading feedback and then improving the course, and it keeps getting better each time, I believe. So help the fourth iteration be even better. Help the next students. So my incentive this semester, if you need an incentive, is if the response rate, by the way, the response rate is the only piece of information I get. Right now the response rate is 31% as of recording this, and I'll update this as I periodically check the response rate. I'll update this number. That's the only number I get. I don't get any information about your course evals, about anything you submit, or even who submitted until after the grading deadline. I still don't get any information about who submitted. It's all anonymous. But I can't even read what was submitted until after final grades are due. So you can have the assurance that anything you say in the course evals will not affect your grade. The university goes to great lengths to make sure that anything you say in there will not affect your grade, so that doesn't alter what you're going to say. We do get the response rate, so we can incentivize you to fill it out. Whether you fill it out because you hated the course or you fill it out and saying you love the course, it doesn't matter. It does. Please say you love the course. But it doesn't matter for this response rate. If the response rate gets to 60%, my incentive is that I'm going to let you complete one of the application objectives from a previous homework, from a deadline that's already passed, until the last day of class. So maybe you didn't get the application objective for homework 1, you were busy trying to learn how the hell Scala works, and you didn't get that application objective. Well, if we hit this incentive, you can go back, finish that one, and earn credit for that, which honestly at this point, after you going through this entire semester and getting all that experience, should be a pretty easy application objective for you at this level of your career. Or maybe you were very close to getting genetic algorithm. I know a lot of you were very close to getting that AO1, the actual genetic algorithm of the GA homework. You can go back, finish that up, and earn credit for it if we hit 60%. And I'll open up submissions on Autolab so you can submit all of those homeworks. If we hit 80%, same deal, but for 2 past application objectives. And you can pick which one, whatever one you missed and you want to make up, go for it. Any 2 if we hit 80%. Yeah, everyone right deserves a raise. You don't have to do that, but if you at least fill out the evaluations honestly with feedback that, especially if you have feedback that can improve the course. If you say, sometimes I'll get feedback that just says, I really hate this, or Jesse doesn't know how to teach, or stuff like that. That's just not very helpful. But if you say, Jesse doesn't know how to teach, when he does slides in this particular way, it's not very effective. But if you present it in this way, like if you gave more examples in the code, or if you did change your slides in a certain way, that's more helpful feedback. But just saying Jesse sucks, brr, that's not helpful feedback, and I don't take that seriously. But if you actually have a suggestion, I absolutely want to hear those suggestions, because it's hard for me to. By the way, I'll talk just for another minute on this, and then I'll get onto the slides. But like as a student, I always thought it was really obvious. Like taking a class, I thought it was really obvious where the professor was going wrong, and where they were doing things that were effective. And I'm just like, why don't they just do this better? It's so obvious that they could do this one thing and just have a much better class. Or if they just change this one thing in their grading policy, things would have been a lot better this semester. I thought it was really easy to see those things as a student, but when Jesse sucks burn. Yeah, now I'm going to see that on the course evals, unfortunately. But but as a professor, like now that I'm on the other side of it, I'm like almost completely blind to those things that I thought were obvious as from a student perspective. I'm completely blind because I'm focused on so many different things now. I'm trying to generate slides and push the slides out, not grade homeworks, but get the graders out for the homeworks, design homeworks, deal with all of the issues that arise in a course, which most of you probably don't even see. I never got to see them as a student, but all the issues that arise in a course, I'm constantly handling issues. And I'm just blind to a lot of the stuff that is obvious from your perspective. So even if you think something's obvious, point it out in the course evals, because I might be completely blind to it. And that can certainly help open my eyes. Something that, you all might even talk about all the time. I might not even know about it. You'd be surprised how blinding it is. Think about giving a presentation. If you ever had to present in front of a class, like you're not noticing like 80% of the stuff that's happening while you're presenting because you're so focused on so many other things. But when you're watching somebody else present, you're going to notice every hand movement, like every awkward sentence. You notice all of that stuff. So anyway, yeah, being a TA will change your views of the course. When you get to see the full picture of a course, that was very eye-opening to me when I first started as a TA and then became a professor. When you get a full view of the entire course, it's kind of shocking, especially if you're like an A student or even a B student. Seeing how much crap we have to deal with is shocking. It was very shocking at first. I don't want to get into details, but it's very shocking. It's very eye-opening. I'll give you one example. Like students who just don't even show up to lecture, never watch the videos, and then want myself and TAs to basically do the homework for them. That's actually very common, and it's very upsetting. And we have to yell at them. And then they get mad, and then they go to rate my professor and say, the TAs won't do my homework for me. It's kind of, I don't know, it's a harsh reality. Anyway, let's get into some juicy content. So today, we're going to learn how to do lecture tasks 5 and 6. Lecture task 6, I created the slides for Friday. I'll officially introduce it on Friday. But you can do 5 and 6 and AO1 after today's lecture. So lecture task 5 is the one we're officially introducing today. This is finding distance in a graph, and specifically in the game. So we're going to find distance while avoiding walls. So, and we want to specifically know how many tiles we have to travel to be able to get from one location to another location. So you have 2 locations in the map, and you have an AI game state as parameters, and you use the game state to find the locations of all the walls and the height and width of the level. You can use my graph method, which, by the way, I did have a bug that some students were running into in my graph method. I did update the repo, so if you poll, you'll get my my latest checks. There was a situation where you could wrap around the edges, and it was throwing some students off. So poll that if you haven't. Or what I did in my testing, I just had a big enough board where we didn't get close to the edges because I just wanted to avoid edges completely. But poll that if you're running into issues with that. And what we want to do here is find the shortest distance in terms of the number of grid locations needed to be traveled to get from the start location to the end location. So the distance between those 2 tiles. That's what we want to compute. No diagonal movements allowed. And we're not computing the path. Computing the path is for AO1. We just want to know the distance between those 2 nodes. So let's get into this and testing. By the way, a lot of you, I'm getting a lot of questions about sees through walls. The incorrect solution sees through walls on Autolab. which it's in the pre-lab document. I give you a test. I explain a test that's going to take care of that one. But it's targeting the closest player. Sorry, this is for LT6. I should have specified. For LT6, it's targeting the closest player based on L2 distance, just like you did in LT1, instead of the closest player while avoiding walls. Like the whole goal of LT6 is to do that. Find the closest player while avoiding walls. So if your tests, the correct solution in your test is always the same as what your LT1 closest player would return, then you don't have good tests. Like you could have just ran your LT1 code and it would have passed your test. So that's what that test incorrect solution is testing. Literally, did you do the thing? So keep that in mind if you're asking that. It's I gave that to you in the pre-lab doc also, but and it is literally what you're doing with LT6. But anyway, I understand why we get that question a lot too. All right, so let's talk about paths. I briefly defined these in the previous lecture. So let's talk about paths a little bit more. A path is a sequence of nodes through a graph where any two adjacent nodes in the path are connected by an edge. So this going from Lincoln to MIT to Utah, SDC, RAND, UCSB, SRI. This is a valid path because all of those nodes are connected via edges. This is a path that we can take and travel through this graph and travel through those nodes. The length of a path, and this is the length measurement that we use for LT5, LT6, and A01. The length of a path is the number of edges needed to be traversed in that path. It's the number of edges in a path, which is equal to the number of nodes minus 1. So this path has 7 nodes in it, 6 edges. So the length of this path is going to be 6. Using Manhattan distance and not path distance. Yeah, it's usually the same for closest player. There can be cases where Manhattan and L2 distance isn't the same though. And you should have a test case in your LT1 stuff. I don't think I forced it just because it's a little tricky. But Manhattan distance is actually L1 distance. It's the sum of the squares, sum of the differences in X and Y. And you can think of this like L1, L2 distance. You probably haven't heard of those quite yet. I don't think they really use that terminology in high school. But it's the nth root of the sum of the differences raised to the nth power is the Ln distance. So L2 is the square root of the sum of the squares. L1 distance, which is Manhattan distance, or city block distance, they sometimes call it, is the sum of the differences, because you can't go through the buildings, you have to go around the buildings through the streets. L3 distance is the cube root of the sum of the cubes, and so on, and it goes on and on like that. That's where those terminologies come from. Yeah, Manhattan distance, city block distance, L1 distance, those are all the same thing. All right, so the distance that we want to talk about is distance in a graph. Distance in a graph is the length of the shortest path between two nodes. So like the distance between Lincoln and SRI, even though we had that path of length 6 that we saw in the previous slide, the distance between those two nodes is actually 3, because there exists a path of length 3, which is the shortest path between those two nodes. We can go Lincoln, MIT, Utah, SRI. That's a path of length 3 connecting these, and no matter how long we stare at this graph, we can't find a path between those two nodes that's shorter than length 3. So the distance between Lincoln and SRI is 3. RAND and BBN are connected by an edge. So the shortest path between RAND and BBN is just take the edge. So the distance between RAND and BBN is 1, because there exists a path of length 1. So for LT5, this is the distance that we want to use, is the length of the shortest path, or the least number of grid locations that need to be traversed to be able to reach the destination, go from start to destination. If the enemies are all ghosts and can move through walls, it'd be a lot easier to code. Just move directly towards the player, regardless of anything else. Be a lot easier to code. Get an AI to avoid walls. Take some not necessarily graphs, but graphs is the common solution. All right, so that's what distance is. How do we find distance? And of course, we're going to use BFS because that's the only graph algorithm we know. We're going to use BFS, and there's a reason we learned it, it's so we could do pathfinding. We're going to use BFS to find the distance between nodes, and we're eventually going to find paths. We're going to go all the way from LT5 to A01 in today's lecture. You're going to be equipped to do everything else that you need to do for the assignment. So let's use BFS to find distance between nodes and actually do pathfinding. So when we run BFS, we're going to run BFS again, except this time I'm going to keep track of the paths that were traveled to be able to explore each node. And just to switch things up so I'm not always starting at UCLA, I'm actually going to start at Carnegie this time. So we're going to start at Carnegie. And what I'm going to do is over here, I'm going to generate a tree that's going to contain all the paths from Carnegie to any node, which will be the paths that were taken to explore each node. So we're going to run breadth first search. Starting at Carnegie, explore all of the nodes adjacent to Carnegie. And when I explore those nodes, I'm going to add them to my path, my breadth first search tree, I'll call it. And I'm going to draw these in tree fashion, like each child is going to go downward visually. And this is kind of subject to gravity in a way, if you want to think of it like that. I'm going to draw this in a very specific way to resemble a tree, with where each node has children, and the children are the nodes that were explored through that node. So when we explore the neighbors of the nodes we just explored, Harvard and Case, we're going to explore all the neighbors here. Find Lincoln and BBN. Now we're going to explore MIT. We're going to break ties arbitrarily, however we end up coding our algorithm. That tie is going to be broken arbitrarily, whether we visit Lincoln or BBN first. For my slides, I'm going to assume that Lincoln was the node that found MIT. So we take this edge. When BBN explores all of its neighbors, Harvard and MIT are both already explored, so it does not re-explore those nodes, but it does explore Rand. And keep going. Each time we find a node from another node, we're going to add those as child nodes in the tree. Now we have 3 different nodes that could explore SRI, so any one of them can explore it. It doesn't matter which one, at least for our purposes for finding distance. We're going to assume Utah found it. Utah was explored first, and UCLA made it to Stanford. Imagine if the Ghost and Pac-Man could move through walls. I almost had Homework 4 be a Pac-Man clone. Maybe someday it will be. Because Pac-Man's interesting, because all 4 ghosts have make different decisions. So we could have 4 different decision trees, one for each ghost. And they all actually behave differently. Fun little factoid. I don't know why I even know that. I think I was just watching YouTube one day, and they started explaining about Ghost AI and Pac-Man. But for top level players, they know exactly how each ghost behaves and what decisions they're going to make at any given time. And all 4 of them behave differently. I get sucked into the YouTube algorithm often. I have to be careful about what I click. I watch a video on one topic one time in my life, and YouTube will be like, "Oh, you love that topic now. Here's all of the videos about that." And it takes forever to get away from that. It takes forever to get off of a topic. Once you click one video, it's a huge commitment with this algorithm. All right, so I have this tree that I drew in this very specific way, our start node, and then each time we explore a node, that's a child of the node from which we explored it. And there's levels to this thing. So if we mark our first starting node, if we mark this as level 1, and then all the children of level, or level 0, and all the children of level 0 nodes are level 1 nodes, and all the children of level 1 nodes are level 2 nodes, so on and so forth. We can mark these levels, and these levels exactly correspond with distance. So a node, for example, a node on level 3 has distance 3 from the starting node. All these nodes on level 4 have exactly distance 4 from the starting node. And in fact, these paths through this tree are all shortest paths. When we break ties arbitrarily, that means there are multiple shortest paths. But these are each a shortest path. This path from Carnegie to UCLA is a shortest path from Carnegie to UCLA. It has length 4, so that it's distance 4 from Carnegie to UCLA. For example, like MIT, we explored it through Lincoln. We could have also explored it through BBN. If this edge wasn't here, and instead that was a child of BBN, MIT is still a level 3 node, and still has distance 3. So you run breadth first search. It's hard to get the D. And whatever level you explored a node on, that's the distance. So you start at your start node, you run breadth first search, you look for the level of your end node, bam, there's your LT5. So that's all well and good on a slide, but how do we do that in the code? So we're going to pull in another data structure here and do this same thing, but in the code. Because visually, yeah, great, it works in the slide, but let's code this up. So let's pull in a map data structure. And what I want to remember for each node, I want to remember its distance. I want to record its distance when I explore it. And we can do this in a pretty simple, I think pretty straightforward way. We're going to initialize all the distances to whatever. I'm just going to initialize them to infinity. Or since these are ints, maybe max integer or -1 to denote that that we haven't seen that. Bellman Ford. No, it's not quite Bellman Ford. We're not that fancy. We're just running breadth first search. So by the way, breadth first search, this only works when you're counting the number of edges. Once the edges have weights, like maybe this edge takes 3 units to traverse and this is only 1 unit. So maybe if our map had like mountains that where you traveled slower and roads where you travel faster, things like that, we can't use breadth first search anymore. We'd have to use something called Dijkstra's algorithm or A star. And then once those edges can have negative weights, then we have to run Bellman Ford. And those are all different algorithms, which you're going to enjoy learning in 331. Right now, we're doing the simplest thing, breadth first search, which will find the shortest path in terms of number of edges. That is an important distinction. This only works when your shortest path is a number of edges. Number of edges. And we don't do A star in 331, by the way. Dijkstra's is a specific implementation of A star, and you do learn Dijkstra's. So the data structure that I have is going to remember the distances. I'm going to initialize this where the start node has distance 0. To get from the start node to itself, we don't have to travel any edges. We're already there. Distance 0 from the start node to the start node. And these distances are going to be the distance between the given node and the starting node. So we're always going to find the distance from the starting node to any node in the graph. And if we want to find distance from another node, we just pick another starting node and then rerun breadth first search. All right, so we initialized the starting node with 0 distance. And now, every time we explore a node, we're going to look up the distance of the node from which it was explored and give it the old +1. So we explore Harvard and Case through Carnegie. Carnegie had distance 0. Add 1. Distance to Harvard or Case is 1. And here, up here, I'm visualizing the queue. This is the order in which we're going to explore the nodes. And the way the queue is set up, whenever we explore a node, we're adding it to the queue. And this has the property that we're always exploring every single node of a particular level before we move on to the next level. The queue just kind of magically, or rather mathematically, takes care of that for us. So we put our level 1 nodes here. We're going to explore both of our level 1 nodes while adding level 2 nodes to the queue. So we're going to explore Case, find Lincoln. Lincoln was explored from Case. Case has distance 1, so Lincoln has distance 2. Add it to the queue, and we have a level 2 node in the queue. We're going to explore Harvard, find BBN, add it to the queue. BBN has distance 2 because Harvard had distance 1. Yeah, no recursion for this. I have my breadth first search code in the repo. I don't use recursion for breadth first search. For depth first search, we would use recursion. But that's not something we've talked about in this class. And then now we only have level 2 nodes in the queue. We're going to explore our level 2 nodes. Lincoln finds MIT. MIT says my distance is going to be the distance of Lincoln, because Lincoln is the node that discovered me, +1. BBN is going to find Rand. MIT and Harvard are already explored. So we're going to find Rand. Distance 3 because it was found through a distance 2 node. Now we have our level 3 nodes in the queue. Explore MIT, find Utah. Utah from MIT, 3 + 1, distance 4. Rand is going to find 3 nodes, add them all to the queue. And those are all going to be level 4 nodes, distance 4. What about width first search? I mean, that's pretty much what BFS is. Breadth, width, kind of the same thing. I know you were making a joke. I gave you the straight answer. And then we keep going through the queue. Utah is at the front of the queue. We find SRI. SRI is going to have distance 5. UCLA at the front of the queue. Stanford is going to end up with distance 5 as well. Nothing else to explore. According to the code, UCSB, we're going to consider all of its neighbors. They're all already explored, which I'm denoting as an orange border here. They're all already explored, so we DQ and do nothing. DQ, DQ, DQ. And now we have a map that gives us the distance from the starting node to any node in the graph. I run this on my starting node for LT5. I run this on my starting node. I run the whole algorithm. I have this map. And then I say, hey, map, what was the distance to my ending node? Look up the ending node, get the distance. Done. Return that. That's LT5. So you're expected to take my BFS algorithm from the repo and modify it to add this data structure to be able to store these distance values and find those distances. Yeah, you use level as graph in LT5. So in LT5, one of the first things you should do is call level as graph. That creates the graph for you. You should look through that code and understand what it's doing. But I decided to give that to you instead of having you write that code. You can write it yourself too. That's fine. You'd learn a lot. But that's my code to take the level and convert it to a graph where each node is a grid location that can be traveled on, so it doesn't have a wall. And then it has edges to all of the grid locations that are adjacent to it, either up, down, left, right, that don't have walls on it. Where's the BFS algorithm? I can't find it. In all good conscience, I can't help you with that. It's in the examples repo that we've been using all semester. All right. Any question on this? Any questions on finding distance with BFS? It's what a lot of you have been waiting for right there. Distance with BFS. There's a distance variable in BFS. I actually removed that. If you pull the latest examples repo code, that distance variable's gone. Because all it's doing is confusing students. Because that distance variable doesn't do this exactly. It actually does the next thing we're going to talk about. But that's what you're supposed to add, is this map that does this. All right, great. But that doesn't super help us for AO1. And if you are looking at that distance variable, this is more of what that distance variable does. Is what we really want is the path. For AO1, we want the path from the start node to the end node. Not just the distance, but the actual path. Distance will get us through LT5 and LT6, but for AO1, you have to actually get the path. So how are we going to do that when we just have these distance numbers? That's not really going to work for us if we're storing the distance values. So there's a neat trick we can use for this. A neat approach we can use is store the actual node from which it was discovered. Not just the distance, not taking that distance and adding 1 to it, but actually store the node itself from which we came. So Carnegie, this is the start node, so we have some value that says this is the starting node. I like to use -1 personally. Some value to denote that this is the starting node, and then for each node we discover, we're going to remember the node from which we came. Lincoln, we found from Case. These two we found from the starting node. Lincoln, we discovered from Case. MIT, we discovered from Lincoln. Rand, we discovered from BBN. So on and so forth. So each time we explore a new node, we're going to remember the node from which it was explored. So now we have effectively the previous node for each node. To turn this into an actual path, we're going to start at a path from Carnegie to any one of these nodes. We'll choose which node we want to target, which would be the node containing the closest player. After running your LT6 code, you get the closest player, find the grid location that that player is on, and then find your path between those two nodes, where that player is and where the target player is. So say we want a path from Carnegie to Stanford. We're going to build our path from the back. As Eric Cartman says, we're going to backtrace through this thing. We're going to start at our target node, add that to the end of our path, and then look at the previous node. Okay, if we were at Stanford, how did we get to Stanford? Well, we got to Stanford through UCLA. How did we get to UCLA? From Rand. So that's the previous node in our path. How did we get to Rand? Through BBN. How did we get to BBN? From Harvard. How did we get from Harvard? From Carnegie. How did we get to Carnegie? Well, that's the starting node, so that's the beginning of our path. And that's how we can build the path. One of these shortest paths, it will have length equal to a shortest path. There might be multiple shortest paths. There are in this case. 1, 2, 3, 4, 5. Are there multiple paths for this one? There might not be. Yeah, I don't think there is a shorter path for this specific one. But we will get a shortest path from the start node to the end node. So it's like tracing your ancestral tree. I mean, kinda. I don't know if that analogy is gonna be helpful or more confusing, though. You can hear those birds? Yeah, they're outside the window. All right. This board looks a little bit different, just different coloring, but the same point is here. Is for our current game. That's fine with graphs. We can find distances through graphs, but we don't have graphs. We have levels. We have... I like the atmosphere. I'm keeping the birds. I ain't closing that window. Plus, I want some fresh air. We want to find paths through a map like this with walls, where this player can move on any green tiles and can't move through the wall tiles. As long as the birds don't hit me with DCMA. So this is what we actually want to do. How do we apply graphs to do this? Well, we're going to convert the level into a graph. This is what my level as graph method does. It gives you a graph where each tile that you're allowed to traverse is a node, and it has edges connecting to each adjacent tile that can also be traversed. So it won't have any connections to wall tiles. And in fact, I don't even add wall tiles to the graph in that method. The way I wrote that one, these nodes for the walls won't even exist. So with that, now we have a graph where we can find, okay, I'm right here. I can find which node in the graph is associated to this grid location. I can find the closest player. Maybe the closest player is right here. I can get their grid location. And then I run breadth first search, starting at me, explore all these nodes until we find that target node, or just run the whole breadth first search on the whole graph. And then go to this node. Okay, node containing my target player. Give me a shortest path. Backtrack. Okay, you were discovered from this node, was discovered from this node, and backtrack to find this path in this graph. And when we're finding paths like this, we're finding the paths in the graph. So even if the player was like here, we're going to be able to traverse and find that shortest path to that player while avoiding any walls, because we don't have any edges leading into a wall. So there's no option to be able to find a path that goes through a wall because those edges are not in our graph. Yeah, I take care of wall location. You should take a look at that method, especially if there's something in there that doesn't fit the way that you're running your BFS. You should understand how that method works. But I did help you out and give you that method. So what we see when we play a game is this. What the computer sees, what the AI sees is this. They see a whole different world. They see these representations of the state of the game in terms of data structures, in this case a graph. And then this is how the AI can navigate a level by using this graph and running algorithms like breadth first search, and for realistically for modern games going to be something like A star or something more complex than breadth first search. But the AI is going to have some data structure representing the level and then run their algorithms based on that. Oh, we actually have 6 minutes left. Any questions on that? Like, so on LT5, you have your game state, which has the level as graph method. Convert the level to a graph. Find those two grid locations in the graph, which for our case means what's the grid ID, what's the graph ID for those two nodes, which I have a function in the code that I give you. I have a function that converts grid locations to IDs in the graph. So you can take that function, throw your grid locations into that function to get their IDs, because the graph just works with those integer IDs, not grid locations. Run breadth first search starting at the start node. Keep track of the distance. Add a data structure that keeps track of the distances. And after breadth first search runs, ask it, hey, data structure storing all the distances. What was the distance to the end node? Return that value and you're done. You're out of there. You're out of LT5. For LT6, you call your LT5 code on each player to find the closest player. And for AO1, instead of just returning the distance, for AO1, you got to combine quite a bit of the methods that you've written. Locate player, find where you are. Locate player to find where the closest player is that's returned from LT6. Call LT6, find the closest player first. And find both of those locations as grid locations. And then run your breadth first search. Take your breadth first search that you ran for LT5, modify it more to actually return the path instead of just the distance, and then return that path. So you're fully powered up to be able to complete all three of those. Which function is that? You got to read the code. It's the only function in that method. And this is the problem. This is why I'm always hesitant to give away too much code, because I get questions like this that basically say, I don't understand the code you gave me. You have to at least read through that code and understand it.